So let T be a normal operator on H, a Hilbert space H. Then the spectral theorem, which is theorem 4.30 in the book, tells us the following. First, consider the continuous complex value functions on the spectrum of T, and this fractor C sub T, which is the C-star algebra generated by T, and that itself is a subalgebra of LH. This C-star algebra is star isomorphic to the other via the Gelfand map. So recalling that and recalling the functional calculus for T, we see that for a phi, which is a complex valued, continuous complex valued function over the spectrum, we generate a an operator in CT just by taking gamma inverse. And note that this phi is a continuous function. All right, so for 443, we're going to consider extending the functional calculus. And although we don't have the tools for it yet, we're going to see why doing such a thing would be useful. And also, why is the functional calculus useful in the first place? Especially for operators with a finite spectrum. So let's consider exactly that. Let T be a normal operator with a finite spectrum. That just means that the spectrum is some set of lambda 1 all the way up to lambda n. So let lambda I be in the spectrum and consider its associated characteristic function, which we'll write chi sub the singleton of lambda I. And given a complex number z, it spits out 0 if z isn't equal to lambda I, and 1 when it is. So this function is actually continuous on the spectrum. And to see this, note that while the spectrum is a subset of C, and the topology it has is the subspace topology, but since it's finite, then it's completely disconnected, and thus the topology it inherits is the discrete topology. So really, when you're looking at complex valued functions over the spectrum, we see that every function is continuous, just because its domain has a discrete topology. Right, so in particular, these characteristic functions associated to the lambda i's are all continuous as well. So what does the functional calculus tell us? Right, let's take a look at these continuous value functions on the spectrum and pass them to CT, right, the commutative C-star algebra generated by T. So this will actually tell us that they land on projections. And so to see that, let's consider EI squared. Now when we pass that back through gamma, that lands on chi squared, which is exactly equal to chi. So then EI squared is EI. Moreover, when you look at the adjoint and pass it through gamma, right? Just remember, gamma is a star isomorphism, so that lands on the adjoint of chi, but chi is a real value function. So that's exactly chi. So E sub I is a projection. Moreover, when we look at their sum, we can pass that through gamma, right? And we get the sum of the chi's. But they're disjoint, so that's exactly chi of the union of these singletons, which is just 1 on the whole spectrum, right? So this function is the multiplicative identity, and since gamma inverse is a star isomorphism, it sends 1 to 1. 1 in CT being the identity operator on the Hilbert space. And now we have that these are equal. This equality will become useful in a second, but first let's define M sub I to be the range of the projection E sub I. Then, because of proposition 4.19, we have that these M sub i's are pairwise orthogonal and they span H in the sense outlined in this very proposition. Now, since E sub I is in CT, the C-star algebra generated by T, and this C-star algebra is actually commutative, EI and then T is T times EI. And then, because of proposition 4.42, at the very end there, right, we have that they commute, which is what the fact that we just mentioned, and that happens if and only if each m sub I is a reducing space for t. Now, considering the identity function on the spectrum, which sends lambda I to lambda I, we can decompose that function in the following manner. And passing that to Ct, well, because of linearity, we find that that lends that sum of the projections, whereas if we pass it directly, well, that just lands in T. Therefore, T is that linear combination of the projections EI. So, inspecting what T does to the subspace Mi, we see that that is exactly scalar multiplication by lambda I. So equivalently, Mi is an eigenspace for T, and each lambda I is an eigenvalue of T. Moreover, we say that the dimension of Mi is the multiplicity of lambda I, which will denote n sub I. Now this implies something very interesting, which is that you decompose the total space into a direct sum of the eigenspaces, and that M should be an H for the total Hilbert space. Now by choosing bases for each Mi, we find that H, not M, can be written as a direct sum of these copies of C in a very special way. Namely, by thinking of T as acting on these copies of C instead of H, write it in matrix form, we find that T is actually a diagonal matrix, namely because the copies of C that correspond to M sub 1, it takes one of those eigenbasis elements and sends it to itself times lambda 1, which is exactly what being in the diagonal means. And that same thing happens for M sub I. And this might be the form of the spectral theorem, which you might recognize. So now let's consider the case when T has a disconnected spectrum, which might be infinite. Now we find that the subspace topology on the spectrum is still discrete, so any function is continuous, including the xi's. So all of that works. Now the problem is you might need a series here instead of a finite sum, which causes our application of proposition 4.19 to break down, because you need a finite sum of projection maps equal to the identity. However, when we look at the difference between the finite sums and the identity, that tends to 0 as m grows to infinity. So while this commutativity thing still works, we just swap out sums by series, right? And so we still get an interesting result, which is that T approximately works as a scalar action on some finite amount of spaces, and so instead of diagonalizing T, we can approximate T with diagonal matrices. However, this whole thing breaks down when we consider normal operators with a connected spectrum, and the problem lies with the characteristic functions. So take, for example, a characteristic function associated to some lambda I. If you consider a small enough epsilon neighborhood around the image of lambda I, which would be 1, well, we find that when we look at a neighborhood of lambda I, the rest of the points in the spectrum are 0 and lie outside of the epsilon ball when passed through F. So the characteristic functions are clearly not continuous. And herein lies the idea to extend the functional calculus. And instead of considering continuous functions over the spectrum, we consider the smallest C-star algebra that contains all of the characteristic functions of these singleton sets. And that is precisely the C-star algebra of bounded Borel functions, denoted by L infinity of the spectrum. Now what really made this work was that C of the spectrum was isomorphic to Ct by the spectral theorem. So we want to extend this Ct to some subset of the bounded operators on the Hilbert space. And spoiler alert, this is going to be the closure of Ct. But Ct is already closed in the norm on the bounded operators of the Hilbert spaces. So this is the closure in a weaker topology than the norm topology. So in the next video, we're gonna be talking about weaker topologies on LH.